Good morning, everyone. So, today we will be discussing the second phase of photosynthesis, which is the light independent reaction, or also known as the Calvin cycle. The Calvin cycle does not require sunlight, but do not be fooled, it's just as vital. It occurs in the stroma of the chloroplast, where energy-rich molecules like ATP or adenosine triphosphate and NADPH, which was produced on the light-dependent reaction, are used to convert carbon dioxide into glucose.
Think of it as nature's food factory, taking raw ingredients like carbon dioxide and combining them with chemical energy to make something more edible. Amazing, isn't it?
The Calvin cycle operates in three main stages. The first process is called the carbon fixation. The second process is the reduction. And third and last is the regeneration of the starting molecules, RUBP or ribulose biphosphate. These steps are powered by the energy you have already learned about the light-dependent reactions.
This slide talks about carbon fixation, a key step in photosynthesis. It explains how plants take carbon dioxide, CO2 from the air, and turn it into useful compound like 3-PGA with the help of enzyme called rubisco. This process is important because it helps make carbohydrates, which are essential for energy. Carbon dioxide fixation basically captures the CO2 from the atmosphere, so it can be used for a reaction. CO2 attached by ribulose bisphosphate, RUBP. Enzyme used for this reaction is called bisphosphate carboxylase or oxygenase, or what we call rubisco. And the result of the reaction is an unstable 6-carbon molecule. Intermediate quickly splits into 2 molecules of 3-phosphoglycerate, 3-PGA, each containing 3 carbon atoms.
This reaction is crucial for producing glucose, which sustains plant metabolism and supports ecosystem. For example, in wetlands, carbon fixation begins when CO2 from the air is captured by rubisco and attached to RUBP, a 5-carbon compound. This reaction creates 2 molecules of 3-PGA, which are further processed in the Calvin cycle to form glucose. The glucose produced serves as an energy source for the plant and is stored as starch, eventually becoming the wet grains we harvest and consume. Carbon fixation is the foundation of life on Earth, converting atmospheric CO2 into the building blocks of energy and growth. Through this process, plants sustain themselves, fuel ecosystems, and provide us with essential resources like food and oxygen. Understanding this step in photosynthesis highlights the incredible organization of nature in supporting all forms of life.
Reduction and photosynthesis refers to the process where carbon dioxide, or chemically known as CO2, is converted into organic compounds, primarily sugars, during the Calvin cycle. In this phase, we are adding electrons and energy to the CO2 molecule. The reaction used for this phase are NADPH and ATP from the light reactions. The 3-PG molecules are phosphorylated by ATP and reduced by NADPH to form G3P, a carbohydrate. The ADP and NADP+ will return back to the thylakoids to convert back to ATP and NADPH by the light reaction. One of the G3P are set aside as the building block of glucose, and the majority of G3P move forward to the third phase of Calvin cycle. Reduction and photosynthesis is crucial, as it involves the gain of electrons, primarily during the light-dependent reactions. Here, light energy excites electrons in chlorophyll, allowing them to reduce electron acceptors, ultimately leading to the formation of NADPH. This NADPH is essential for the Calvin cycle, where carbon dioxide is fixed into organic molecules. This reaction not only initiates the synthesis of carbohydrates but also serves as the foundation for energy storage in plants. Without carbon fixation, plants would be unable to produce the sugars necessary for growth and energy. Moreover, the process not only produces glucose but also releases oxygen as a byproduct, making photosynthesis vital for life on Earth by sustaining ecosystems and providing energy for heterotrophs.
The regeneration of RBP is the third phase of Calvin cycling of regeneration of RBP. In this phase, the remaining DT3 undergoes reaction that require AT3 to regenerate 3 molecules of RUBP, and then the RUBP molecules can combine with additional carbon dioxide molecules containing the carbon reaction. The regeneration ensures that the cycle can continue, allowing for further carbon fixation as long as CO2, ATP, and NADPH are available.
But before we come to an end, have you ever wondered what lies beyond the conversion of CO2 from the atmosphere into organic molecules? Well, fun fact. Melvin Calvin discovered the Calvin cycle. He was an influential American biochemist born on April 8, 1911 in St. Paul, Minnesota. He earned his bachelor's degree in chemistry from the Michigan College of Mining and Technology in 1931 and completed his PhD at the University of Minnesota in 1935. Calvin spent most of his career at the University of California, Berkeley, where he conducted groundbreaking research on photosynthesis. Calvin is best known for elucidating the chemical pathways of photosynthesis, particularly through the development of the Calvin cycle, a series of reactions that convert carbon dioxide into glucose using energy from sunlight. His innovative use of the radioactive isotope carbon-14 as a tracer allowed him to track carbon's journey through plants, leading to significant discoveries about how plants synthesize organic compounds. For this work, he was awarded the Nobel Prize in Chemistry in 1961. Throughout his career, Calvin was a proponent of interdisciplinary collaboration and conducted research across various fields, including artificial photosynthesis and organic geochemistry. He authored several books and received numerous accolades, including the National Medal of Science. Calvin passed away on January 8, 1997. Leaving a lasting legacy in the field of biochemistry and plant science.
In summary, the Calvin cycle not only powers the production of glucose, but also supports the broader ecosystem by contributing to the carbon cycle. Understanding this process is essential for appreciating how plants harness energy from sunlight to sustain life on Earth. Together, these processes highlight the intricate nature of the Calvin cycle, showcasing its essential function in supporting life on Earth by providing the organic compounds necessary for energy and growth in plants, and ultimately in all living organisms. Thank you for your exploring this vital aspect of photosynthesis with us.